Welcome to GWA Physics, and the problem that we're going to work next is called the conservation of energy and friction. What we're trying to do is we're trying to see how friction plays an important role in removing kinetic energy from a problem and possibly causing objects either to slow down or completely come to a stop. So in this particular problem, we've got a 0.5 kilogram block sitting at the top of a 2-meter high hill. The block is going to slide down the hill, and in doing so, the potential energy of the block at the top of the hill will be equal to the kinetic energy at the bottom of the hill. We've talked about that in class before. Then, the kinetic energy that the block has will be taken away as it slides across the friction. Let's give this a coefficient of friction of 0.75. And so the block has the maximum amount of kinetic energy at this spot, but by the time it gets to this spot, the friction will have taken away all of the kinetic energy and the block will simply stop. You got to remember that kinetic energy is the energy of motion. And we also need to remember that friction is a force that tries to oppose motion. So let's start out by solving for the potential energy at the top of the hill, and that's going to be equal to mgh. Well, the mass is 0.5, and g, which is the acceleration of gravity, is 10, and the height is 2. So you've got 0.5 times 10, which is 5, times 2, which is 10. So you've got a total of 10 joules of energy at the top of the hill. Now, as that block slides down to the bottom of the hill, all the potential energy is converted, is changed into kinetic energy, or the energy of motion. And so we haven't been asked this question, but we could be asked, what was the velocity of the block when it got to the bottom of the hill? And we would use the kinetic energy formula to solve for that. But right now, no velocity's been asked for. So we're going to let that block slide over here to this spot where it's going to enter into this area where there is friction. Now, you should remember that we had something that said that there is a work energy theorem. And what that says is that the work done by friction is going to be equal to the change in energy. Now, the only energy that friction can remove or take away is kinetic. It does not have any effect on the potential energy at all. So let's work this from the standpoint that we know what the energy change is going to be, because this thing has 10 joules of energy as it begins to enter that frictional surface, and it will have 0 joules of kinetic energy by the time that it stops, because if it's not moving, it has no velocity, therefore the kinetic energy is 0. So now the change in energy is going to be 10 joules. The work done by friction, we simplified this in class earlier, and we said that the work done by friction was going to be equal to the coefficient of friction times the normal force times the distance is going to be equal to the change in energy. And you should recognize this formula from what we did in class. Now, let's plug in some numbers. We've got 0.75 as the coefficient of friction. The normal force, you should remember, is equal to but opposite the weight. So if we go back to this picture over here, this 0.5 kilogram box has a weight of 5 newtons. And if it has a weight of 5 newtons, then the normal force is also 5 newtons, because it's on a flat surface. And it will be on a flat surface again down here. So the normal force is 5 newtons. And we're actually solving for the distance, and we know that the change in energy is 10 joules. So, again, I've set my calculator down. we have 5 times 0.75 is 3.75. D is equal to 10. So we divide both sides by 3.75. This one canceling. And D comes out to be 2.66 repeating meters. And I'm going to put a slash over that to show that it's repeating. Are there any questions about how you solve for the distance traveled based on the amount of friction that's taking away the kinetic energy? Thank you for watching.